use that to your advantage, right? I suggest you use that to your advantage by asking questions, making sure that you are clear, because this is a big chunk of material, and we're going to try to get through the majority of 15 so that we move on. Another thing I'd like to say, I did update the calendar to reflect chapter 15 this week, chapter 16 next week. I think on the original calendar, I had like 15, 15, 15, not realizing that equilibrium is 15, 16, 17. So just realize that. Today we're going to talk about 15. So the best way to put equilibrium is chemical equilibrium occurs when a reaction and its reverse reaction are proceeding at the same rate. So what do we mean by that? And once you understand this is the basis for all of the learning that you do in this class, is that if we have a reaction, and it doesn't matter what that reaction is, but in this case, let's use what they use up here. They use this example of N2O4 turning into 2NO2. I'll do this in blue. That's fine. Up until this point, we have not talked about the reversing of a chemical reaction. We leave that until this chapter. In General Chemistry 1, we only talk about the idea of a forward reaction. What we must know from this point on, and from this point on in all of your chemical understanding and knowledge, is that there are very few instances of what is truly a one-directional reaction, right? Most reactions have a forward, meaning left to right, and a reverse, meaning right to left. And forward and reverse are always going to be that exact same direction, right? Left to right is forward, right to left is reverse. This particular situation says that there is a decomposition reaction occurring of dinitrogen tetroxide into nitrogen dioxide. And that is the forward reaction. Up until this point in our chemical kinetics, we have said that this reaction has a particular order, and that particular order has a rate law that has a particular K. That particular K we know is a function of what? What is K a function of? Temperature and a function of? Right, the type of reaction, the type of molecules that we're dealing with, right? So K forward is a function of the temperature we're doing this reaction at and what kind of reaction we got going on, what kind of molecules we have studying. Now, that we should understand that at this point. We should understand that the Kf is going to be large or small as a function of temperature or nature of reactants. Now, what is occurring in a chemical reaction when we make a product? That is something that this is not something you've been taught to this point. And this is something you must get in your head right now. Is that there is also the possibility for a synthesis reaction to occur in the reverse direction to give us back our original reactant. That is occurring in almost all instances of chemical reactions. In this particular chapter, that is the focus, both ways. Now, what about the rate of this reaction in reverse? We can treat that the same way that we treated it in the kinetic situation last chapter. It has an order, it has a rate law. Right now we're not so worried about the order and the rate law, but that K is a function as well of the temperature you're working at and the nature of this reverse reaction, which is now a synthesis and not a decomposition. Right? This needs two molecules to interact with one another. This forward needs one to decompose. So there's a different nature, which means that we should see a different K for each. Okay. So make sure you have your head wrapped around the idea that forward and reverse reactions are happening with a rate constant for each that is most likely different, and it is due to the nature of each molecule or molecules that are reacting. Now they show you this graphically, okay? And again, graphs are not something that I feel like a lot of students come into my class and are strong with, but I try to use them so that you can leave here and have a good understanding graphically. So what they've done here for you is to show you that at the very beginning of this reaction, what is in our reaction vessel based on that graph. This lets me know if you're reading this left graph correctly. What is in our reaction container at time 0? Yeah, on graph A tells us what do we have at time 0?
We have the reactants N2O4.
Right. So at time 0, all we have is this guy. That's it. Why do we know that? Because we see that our product for the left to right forward reaction starts at 0. We don't have any reactant yet. So what is this graph telling us? At time 0, we are starting with only reactants. Okay? Now what they say is as time goes along, what do we see happening to the concentration of our reactant? What's happening as we go to the right? Or as time goes on? I mean, not confused. What's happening to our reactant?
Decreasing.
The concentration is decreasing. Why is the concentration decreasing?
It's being decreased.
Right, because a reaction is occurring. Okay, so we have a decrease in concentration because the forward reaction specifically is occurring. The forward reaction produces a product, and what do we see occurring over time to the product concentration? See it increasing. Very simple. Simple and straightforward. Now, we do see an increase and a decrease up until the dotted line. And this dotted line is extremely important because you see that concentration over time, or the change in concentration over time, which is also related to the rate of the chemical reaction, the rate of decomposition of N2O4, and the rate of the reverse reaction, or the synthesis and the making of N2O4, both of those are no longer changing in concentration. What does that mean kinetically? Now this is where you know if you had your head wrapped around this.
The composition remains constant.
Right, the composition of the container remains constant. So what does that say about the rates of these two?
They're equal.
They're converting back and forth at the same rate.
Right. So the rates are necessarily not equal, but the rate of forward and reverse are staying the same. So the ratio of the two are constant, right? So that is the only way to get a graph that looks like this, is for the rates of both of those to no longer be changing as a function of time. Doesn't mean that they're equal, right? Doesn't mean that they're equal. Now, I haven't brought up the word, like I've been using a lot of kinetic terminology, and eventually I'm going to stop because concentration doesn't change. But notice here, the rate of the Kr times this are going to be the same as a function of time. It's hard to say that there, but they are converting back and forth at the same exact rate, but Kf and Kr may not be equal. That's the key here. Kf, Kr may not be equal. The amount or the composition of your container stays the same, and the remaining constant is extremely important once you understand equilibrium. But a lot of people's idea of equilibrium does not involve the back and forth because we haven't brought that up yet. What that means is that we do not have a reaction that's done. And a lot of people think that that's the case. We have a reaction that the forward and reverse are occurring at the same rate, The composition of the reaction is the same, but there are formation and decomposition reactions occurring constantly. That's the key there. So, dynamic equilibrium from a definition standpoint, products are being made, but reactants are being made at the same rate. The total amount does not change. Neither reactant should be able to leave the system. And now, we have some scenarios where they can, but let's keep it simple for now. And then the ratio of the concentration is constant. That's the main thing that you want to take away from equilibrium, because the rates and things of that nature, that's more of a kinetic thing, but we want to talk about the why equilibrium occurs. That's because of the rate, but now we want to move forward and talk about this ratio and the mathematics of a system of dynamic equilibrium. So we should have been able to answer on the in-class worksheet that first question is achieved when they proceed at the same rate. Again, remember, K value for each of those is not necessarily the same. All right. So when I say in the example that I gave you, relate the forward and reverse chemical reactions. So the forward, what I wanted to show there, and they do, I think, in this next slide, is here. What I wanted to show was that in the example that I gave, N2O4, N2O2 2NO, so in the example I gave, I wanted to give you this. And now, if I was to tell you to assume that this was an elementary reaction, what you would then be able to tell me, right, or show me, is that the forward reaction, if it is in fact elementary reaction, the forward reaction here should be what order? Should be second order. Why? Elementary, bimolecular, second order. So, rate of the forward reaction would be equal to N2 concentration times O2 concentration times Kf, right? I'm just writing it at the end. It doesn't matter where it goes, right? It can go on the front or the back. It doesn't matter. All right? Now, if we look at the reverse reaction, okay, what is the order of the reverse reaction? Second order as well. It is elementary, but we have two NOs. So we have the rate of the reverse, which is equal to NO squared, KR. Now, if by definition we do have a system at equilibrium, let's say we did this reaction and I told you it had reached equilibrium, then we must say that the rate of the forward is equal to the rate of the reverse. And what they have done here for a different example, but what we can do for any of these examples, is to be able to relate that if rate is equal to Kf into O2 and Kr in O2, then we can show that into O2 Kf is equal to NO squared Kr. And if we divide and put products over reactants, we see that NO squared all over into O2 is equal to Kf over Kr. These Ks that I'm talking about right now are rate constants, right? Because we're still talking rate. This is going to be probably the end of me bringing up little k though. But I wanted to show you that if these have to be equal, then this ratio of K to K will always be constant at equilibrium. This is only at equilibrium, right? All of this, what I just wrote, is only at equilibrium, which is why we didn't even talk about it in chapter 14, because we hadn't even brought up the concept of equilibrium. So what I just showed you is the derivation of the constant, and that constant, Kf over Kr, little k, is equal to what we are going to talk about from here on out, which is big K EQ, which is also, you may see as big K little c. KEQ, KC. C standing for concentration, because our units in the equilibrium constant are in concentration. So this is equal to, for this particular example, into O2 over NO squared. This derivation, however, realize that I will not be asking you to do this, because this is only holds true in this particular case. To show you it this way from a rate perspective, it only holds true when we're dealing with elementary steps. When we get into non-elementary reactions, the good thing is that we no longer have to think about this, because KEQ or KC is always a function of products over reactants, and these values are the coefficient of the balanced chemical equation. Okay, so let me say that, and I think they talk about that here. Equilibrium constant does depend on stoichiometry, so we have to wipe out of our minds kinetics, because kinetics said you can only determine order by experimenting. Equilibrium says that products, if you have A plus B, gives you C plus 2D, that K EQ is equal to products, concentration of them, squared all over concentration of the reactants. And that is the relationship. They're showing you an example there on the PowerPoint. So we no longer have to know the rate law or any of that. Let's not worry about the rate. I just want to show you how we derive the entire concept of equilibrium. From now on, you're going to see a double arrow, forward and reverse. So you need to be able to look at a chemical reaction and write the expression, hands down, no questions asked. You should be able to be balancing the equation and then write it. If I don't give you a balanced equation, because that's general chemistry 1 for sure. So here's another graphical example, and in this case we're dealing with 3 different molecules. 3 different molecules. The Haber process, a very important process. I think I talked about this with my other class, but Franz Haber was a German guy. Well, he was in Germany. He was the head of chemical warfare. His job was to find something to blow some shit up. His process of fixing ammonia, which is used as an early explosive, right? We know it now as a cleaning supply. But ammonia was used as an early explosive. So what he was able to do is show a process that took nitrogen gas, hydrogen gas to create the explosive that they wanted. He was trying to kill a bunch of folks. That was his main job. What ended up occurring was he was actually kicked out of Germany once they found out that he was actually Jewish. This entire time he was working for Germany. I guess he thought he would be safe as long as he was helping them kill some folks. But they ended up having to send him out of the country because they were going to kill him. His process was, he was trying to kill some folks, but what they ended up finding out is this process is currently the process used to fix nitrogen for fertilization of crops, which is the only reason that the planet can sustain with the amount of humans on the planet. So he was trying to do something bad, ended up working out to be something good, right? And now we have other warfare. This is basic warfare. Now we got nuclear warfare, right? But at the time he thought he was doing something bad. Now this process is very interesting. If you read up on it, watch some videos on it, it's a very interesting process, but they use this to show you again, at time 0, we have products, we have only reactants, and then at some time, we have all 3. and that all three exist in what we call equilibrium mixture, and notice that the concentration is no longer changing over time. Let's say that we only had products. So let's say we were talking about the reverse. The reverse involves only having products. What must occur? All reactions are trying to achieve equilibrium, right? And you think about that, that's kind of a comparison to life, right? We're all trying to achieve some level of equilibrium in our life. We're working towards something that we think is going to get everything smooth and situated. Same thing's going on in the chemical system. If you only have products, then the reverse reaction is going to occur until equilibrium is achieved. And notice that the achievement of equilibrium and when, that's a function that is a kinetic question. We won't have to worry about that in this chapter. The when means we're dealing with time. The time means we're dealing with kinetics. This chapter we're focused on the composition and the understanding of how equilibrium can be affected. But we're not so much worried about the time. That's more of a kinetics question. Here is the situation that I gave you, realizing that remember from kinetics, Kp is partial pressure of C, partial pressure of D squared over partial pressure of A, partial pressure of B. I'm giving a different example than they did, but I'm using a stoichiometry that involves using a superscript of 2. Now, one thing that needs to be said though is this equation is given to you on the reference material, I'm pretty sure. Because gases are using the ideal gas law, we cannot directly relate Kp to Kc. The reason for that is because the partial pressure, where we have more than 1 moles of gas, changes things. So that delta N is moles of gaseous products minus moles of gaseous reactants. We're going to have an example, if we get to it on the worksheet, where we're going to use this. So I'm going to show you in an actual example how to use this equation. But RT needs to be taken into consideration because of the ideal gas law. So this equation is going to be given to you. I'm going to show you in a little bit later how to use it. So all they're showing you here is some data on a given experiment, and they show you that they start with 2 of the 3 components. Excuse me, they start with 2 of the 2 components from our original, and they notice that the equilibrium concentration of each of the 2 components still give you a ratio Kp or Kc in this case that is roughly the same within experimental error. What they're saying is that K is a function of T. K is a function of T, just like Kf and Kr are a function of temperature. Therefore, equilibrium is also a function of temperature. So K is constant. K will only change with a change in temperature. So at a given temperature, it doesn't matter what amounts you throw in, you should achieve equilibrium with the exact same equilibrium constant. Now, how long will it take? It's not for us to be concerned with right now, because some experiments might never reach equilibrium, but we know the equilibrium constant what it should be from experimental. But some stuff will never happen. Like, right, we have hydrogen, nitrogen, and oxygen gas in the air right now. The reaction of hydrogen and oxygen to create water is a forward reaction, right? But why is it not happening right in front of us? It may not be kinetically favorable. The temperature in here may not get us over the activation energy, right? There's a lot of other stuff coming into play. But when we're talking equilibrium and the question examples I give you, realize that we are dealing with, when I say the reaction has reached equilibrium, it doesn't matter how long it took, right? We're not talking about a time. Okay, let's talk about reading the graph. Let's talk about this this graph that I gave, because that's a great question. Application of graph, application of knowledge. So on that question, we're dealing with a situation where we have 2 reactants, I think. And, oh, sorry, excuse me. We have a single reactant and 2 products. All right, let me zoom in so I can see a little bit better. Okay, we have CO, CO2, and CO2 and CO, right? So we have a decomposition reaction occurring, CO, CO2, CO plus CO2. All gases, and we see a enthalpy value is equal to some positive value. What does that mean? Drink in one, positive enthalpy. No. We call this endothermic. And exothermic is negative. Okay, so we got an endothermic reaction. That means that energy is released. That means it takes energy to get this to happen, right? Okay. Now, if you look at the graph, at 0 time, do we have molecules of everything? Question. So we're looking at question 3 right now. Do we have a concentration of all these gases at time 0? Yes, we do. Now, from between time 0 and time 4, what is occurring?
Constant rate.
Okay, constant rate. Or you could state that the concentration is not changing, right? Constant rate, same thing. But what I want to try to get you to start thinking about is more so an equilibrium look at, right? So you're correct with the rate, but don't get rate. We don't want to try to bring the two together, right? The purpose of this class would not be to bring them together. You do that kind of some upper level stuff, because kinetics and equilibrium together is a monster, right? It's hard enough separated. But the better way to think about this, to be on a more equilibrium-based viewpoint, is concentration is not changing, right? So, therefore, the answer to question A, I asked you, is the reaction at equilibrium at T equals 0 minutes? Is that a yes or a no? Yes, okay. How do you know? That would be what I had stated as the answer. The equilibrium, concentration of all constituents are not changing. So none of the products or reactant concentration is changing. So this graph is a very good graph to show us that between 0 and 4, nothing is changing. No concentration changing. Okay, now let's talk about 4 minutes. At the 4-minute mark, what has happened? And this is going to take some little graphical intuition. At the 4-minute mark, what has happened? Mind you, this is at a constant temperature, so take that into consideration. If the temperature is not changing, what does the graph tell you has occurred at 4 minutes?
That means the constant equilibrium has changed too, right?
Well, we can determine that. So before we move forward, let's do a quick calculation of the equilibrium constant. So what is K? What is the equation for K for this example? So KEQ is equal to what? Specifically, concentration of CO times concentration of Cl2 all over concentration of CoCl2. Now, do we currently in our graph have the information to calculate this? At time 0, yeah. So if we want to talk about this at T equals 0, or at the beginning of our reaction, you don't have to say time. We can look at this and say we got 0.9, or excuse me, we got 0.09, 0.07, and 0.055. So let's say we got 0.09, 0.07, and 0.055. All right, and that's just me eyeballing it, right? You could get some values that could be a little bit different. Once you plug this into the calculator, you get uh, 0.115. All right, there are no units in KEQ or KC or KP. There are no units. Now, this is one of the few times where you have to just take my word on it. I'm not going to go through the reason and the derivation why. In your textbook, it does do a good job of explaining to you why there are no units in K. It's because these concentrations are actually technically converted into activities, and the activities are all divided by molarity, which leaves you with no units. So KEQ is always unitless. It's one of the few unitless values, kind of like a mole fraction. Unitless. All right, so if we took a look at the values of equilibrium, tell me something. Do we reach equilibrium? So at minute 4, something is happening. So let's hold that thought for a second. We don't, maybe nobody's answering what they think is happening. So let's hold that for a second. If we took a look at each one of these, what do we see? We see an increase in the products. We see an increase in the products, and we see a decrease in the reactant, right? So what had to be occurring? Something has to occur for us to shift this equilibrium. So we're talking about the equilibrium shift in a second. Now, when do we reach equilibrium again, or do we reach equilibrium again?
Time 8.
Okay, at time 8, it looks like we reach equilibrium again. So let's take a look at those values at 8. And those values looks like 0.11, 0.085, and 0.04. So 0.11, and let's say 0.4-ish. Yeah, okay, so if we take a look at this number, what do we have? All right. So, what did we say about a reaction at a particular temperature? What did we say about K? K should be,
Going up, increasing.
at a given temperature, K should be,
Is 0.04
oh, I got you. Yeah, I used the wrong thing. Hold on. 0.11 times 0.085 divided by 0.04. Excuse me. You're right. This should be 0.0. And this should be order of magnitude, so 2, 3, 4. All right, sorry about the number. So if K is constant at a given temperature, then, and I tell you, let's assume this is at the same temperature. And why are these two different? And I'm not expecting you necessarily to know this, but let's think about this. What did we say? Everybody said at 0 to 4 we were at equilibrium. I'm going to say that we're not, so I'm not trying to trick anybody. I want to see kind of how you interpret data, right? Because data interpretation is important. So I think what they're trying to give you and show you is that at 0 to 4, we had our CO, Cl2, and we had our CO and Cl at a constant.
At rate, but not.
No, not a constant rate. We had them at constant concentration. We had not started any reactions yet. Okay, right? For a reaction to occur, these have to be interacting with each other. So, at time 4, let's say that we open this vessel up, and now we have reactions occurring. Okay, so that's what effectively they're trying to show in 4. But I just wanted to start to incorporate more graphs. So they're trying to show you that something is happening at 4, and it had to be the introduction of reactants to products to start equilibrium. So this is not KEQ, right? This is not KEQ. This is more what we're going to talk about in a little bit. This is more so Q, what we call a reaction quotient. We're going to talk about that in a little bit too. This is going to be Q. So let's treat A as KEQ for our value. This is going to be our important value for this. Now, at minute 10, what happens? From an interpretation standpoint, in a chemical, in a laboratory type setting, what happened at minute 10?
Another reaction.
Well, look at the data. What does the data tell you that happened? This is where data interpretation. From a graph, what happened? What had to happen right here at minute 10?
The amount of CO2 was used up.
The amount of what?
The CO.
Okay, the amount of CO changed, right? Okay, did it go up or down?
Down.
Okay, it go down. And look at our decrease. That decrease was very sharp, right? It happened right at that moment. Instantaneously. So what does that mean from a practical standpoint? You removed it, right? So you removed CO, right? That was what was done in this graph. Removal of CO. So essentially what we said is we found a way to just take out one portion. So at minute 10, we see the taking out of CO. And then we see we see the forward and the reverse reactions occurring to create equilibrium again. So let's take a look at okay, tell me at what time do we reach equilibrium after the 10-minute mark? 12. At 12, right, at 12. So we are looking at 0.12, 0.06, and 0.03, right? Yeah, 0.12, 0.06, and 0.03. Now, theoretically speaking, if we have not changed any temperature, right, and we have not done anything differently to our container vessel, this value should be what? Should be the same. Now let's hope that the makers of this plot, because I didn't make this plot, let's hope the makers of this plot were able to achieve that. Ah, right. So we got 0.24. Within experimental error, right, these two represent the same, right? So what that tells us is that first calculation we did, we were not at equilibrium. We had not started a reaction yet. The first calculation of equilibrium constant at time 8 gave us a value. We removed something. We allowed equilibrium to reestablish, which is what the language there will be, and that gave us the same value. Okay, so what happened at 14? Right, we removed a little bit of everything, right? We remove some of each of them, which means we open the container and then close it back, right? Think about this practically. I'm trying to make sure that the lab and the lecture kind of coincide a little bit. So it looks like they just opened it and then closed it. And it looks like maybe Cl2 flew out a little bit faster, right? CO2 flew out a little bit slower, but if you think about kinetic molecular theory, it should make sense. The bigger stuff is moving slow, right? This was a beautiful graph. As soon as I saw it, I said, man, this is great. So if you removed all of that, then equilibrium should be reestablished once again at minute 16, and we see that we should get a KEQ of 0.085, 0.045, and 0.015. 0.0854515. And that should be roughly the same. Uh, 0.25-ish. Again, now these are all roughly the same, right? In a real experiment, right, they're not always going to be spot on, right? We got experimental error. But what this graph is trying to show you is that equilibrium will be reestablished. How long it takes, not really of our concern. More so, we need to be able to see that. If I give you something graphically, you need to be able to see that. So the equilibrium constant and calculation of the value. And now let's talk a little bit about the idea of the magnitude of K. So part D of this question goes back, let's go back to the slides for a second. If K, from a numerical standpoint, is greater than 1, meaning 1 or larger, then we have a ratio where the numerator is bigger than the denominator. Hopefully we understand that basic math. So if the numerator is bigger than the denominator, then that means the products, or what's on the top, which is always products, is larger concentration than the reactants, which means that we're dealing with a reaction that favors the products to the right. So what we say is that the equilibrium lies to the right if K is greater than 1. If K is less than 1, then right, the denominator is larger than the numerator. Therefore, the reaction lies to the left, and what we call reactants are favored. So you need to recognize both those statements. Reactants are favored, lies to the left. Products are favored, lies to the right. You need to be able to know each of those and which one they correspond with. So, part D, to our question, given our value of KEQ, this reaction equilibrium lies to which direction? To the left, right? It favors the reactants. Favors the reactants. Now, real quick, let's take a deep breath, because we covered a good chunk of material right there. I tried to condense it because we're not working with a whole bunch of time. Try to condense a lot of material. Where are there questions, clarifications needed, understanding conceptual questions? This is a very conceptual chapter that involves a lot of math, but the conceptual portion, having that foundation, is going to help you in the long run. Any questions, clarifications needed? Another example, yeah.
So for A, the answers change now that it isn't at equilibrium.
Right. The A is not at equilibrium. How do we know that? We needed to calculate KEQ at 8 minutes or whatever. And we know that those values are not the same. So how you know that is that the values from time 0 to 4 are not the same values at time 8, right? Mm-hmm. That's why. Any questions? Are we sure and confident that we can be given a chemical equation, balance said chemical equation, determine KEQ, and from there, calculate KEQ? Right.
Question. Go back over why it lies to the right or the left.
Okay. So, in the case of a chemical reaction, let's just say, okay, let's talk about the decomposition of water, right? So, if we had a effective and efficient way to do both of these reactions, the forward and the reverse, we would never have any energy issues in the entire planet, right? We would not have to pay, well, you'd have to pay, but we wouldn't have to worry about fossil fuels, we wouldn't have to worry about digging in the ground, messing up the environment, messing up the air, right? Because hydrogen and oxygen gas is all around us, right? Water, there's a constant composition of water on the planet, pretty constant, right? It's been the same amount that's been here since before, because it goes into the atmosphere and then comes back down, back and forth. Either way, let's say we could decompose water. Very tough to do, right, without having power. This reaction at equilibrium, let's say, I gave you some concentrations that were, or let's do this in gas, let's do this in pressure to try to incorporate some other stuff. Let's say that I gave you the partial pressure of H2O is equal to 3 atmospheres, and I gave you these are equal to 0.05, and partial pressure oxygen equals 0.001. I don't know. And both of these atmospheres, I'm just making some numbers up. Now, if you were to determine Kp, right, then Kp be equal to what? This is just more practice on setting up the equation. What is
It's the P of the products.
right, P of the product. So partial pressure of H2 squared times partial pressure of O2 all over partial pressure of H2O squared. So you got to be able to write this, right? You don't write this, you're never going to get any of the math right, right? Because the math is the function of the proper expression. So here's your Kp expression. Now that you've written the correct Kp expression, remembering that these 2's are right here. Okay, that's where those 2's come from. If we then plug in these values, we see we end up with 0.05 squared times 0.001 all over 3 squared. And if you do the math here, .05 squared times 0.001 divided by 9, 3 squared. So it looks like 2.7 times 10 to the negative 7. Or 2.78, however you want to look at that, 2.8. All right, now, from a magnitude perspective, is this a big or a small number?
Small.
Right, it's a small number. So a small number, or a number that is less than 1, says this numerical value tells you the nature of this equilibrium interaction. It tells you that at equilibrium, or when this chemical system is happy, if you will, right? If everything's trying to reach equilibrium, and once it reaches equilibrium, it doesn't do anything else, and it's happy, this equilibrium exists. When it's happy, we have a very small value, which tells us that water is favored in this reaction, which means that it lies to the left of the arrow. Lies to the left. Now, why does it lie to the left? Nature of reactants K value for the rate constant. That's why. But from an equilibrium standpoint, all we have to be able to say is the lies to the left. How do we know that? Kp is less than 1. So what do we expect in this system? And then that's a great, so now I'll ask you this question a different way, without any numbers, right? Well, without having to do any of that. Let's say I gave you let's say I gave you this scenario, gases, and let's say I told you that K EQ for these is equal to 2.5, and then I ask you, the conceptual question is, what do you expect to dominate in a equilibrium mixture another way to ask the same question? In an equilibrium mixture of this reaction, what do you expect to be in that equilibrium mixture? What do you expect to be dominant? What do you expect to have the most of? Products. Products. Why? Because this is greater than 1, therefore equilibrium lies to the right. Therefore we should expect to see a bunch of products, not that much reactants. Right? And that's just a generic statement, right? But it holds true for everything. And again, the direction, the forward and reverse is the reciprocal, right? So if we wanted to look at KEQ for the reverse, it would have to be 1 over 2.5, right? It's the reciprocal. I don't normally ask too many questions about that. That's not as applicable. Neither is this. These two, not so worried about the stoichiometry. I'm not going to be asking you to square everything. I'm not worried about that. It's more so about being able to write the expression, being able to deduce something from the expression, and then don't worry about consecutive equilibria yet. We'll talk about that if we need to in the acid base or the additional aspects. So let's not worry about those 3 slides so much in this particular portion. This particular portion. And then, real quick, and then we'll take a quick, like 5-minute break, I guess. 5-10 minute break. Homogeneous versus heterogeneous. So all the situations that we've talked about thus far, everything has been in the same phase. They would have either been in the gas phase or they're in the aqueous phase, right? But some chemical reactions that you deal with have heterogeneous equilibria, which means that some of the stuff is in a different phase. And this brings up the concept and the idea of how do we put and relate solids in an equilibrium expression, and the concentration of a pure substance, whether it be a solid or a liquid, is always 1, right? It's always 1. So, for the example that they use the decomposition of calcium carbonate. And if you look at that decomposition, we have calcium carbonate, which is a solid. Anybody know what that's called? It has a common name. Now, baking soda is sodium bicarbonate.
Bicarbonate.
Calcium carbonate is known as limestone, which is why limestone as a rock, it goes away because of this reaction. Limestone goes away, turns into calcium oxide, and then CO2. So limestone kind of degrades over time. Now, this is a reversible reaction, which means that the same forward and reverse reaction are occurring, but what we see is that as calcium carbonate decomposes, we create a gaseous product. And if we look at KEQ for this, or KC, however you want to show it, just realize that you need to be able to differentiate between KP and KC. KEQ is equal to concentration of CO2 times concentration of CaO all over concentration of CaCO3. And I'm going to show you why this is not a valid expression. Okay? A lot of people are going to use, on a quiz, when I give you a question about writing the expression for a heterogeneous equilibria, a lot of people are going to write this and it's going to be wrong. Okay? The reason for that is that what is concentration, by definition, is what? Moles per liter. Okay? Moles is a function of grams over molecular weight per liter. Okay? If we take a look at a pure substance, let's look at the reactant, calcium carbonate. Calcium carbonate is a solid, and that solid has a particular density. Therefore, if we had a density that's grams per liter, grams per milliliter, the density of this does not change. Therefore, the concentration of a pure substance will never change, right? Concentration of a pure substance will never change, which means the concentration effectively becomes 1, which means that both of these go to 1, which means that the KEQ expression should only involve non-solids or pure substances. So solids never show themselves in the KEQ expression, and then the KP expression obviously is the partial pressure of CO2. If you ever see water, and I won't talk about this so much until we get into acid-base equilibrium next chapter, but water, pure liquids are the exact same, right? Pure liquids are treated the same. They are not in the equilibrium expression. All right, let's take a quick break. Stand up, walk around, grab some water. Let's come back at, let's come back at 4:20. And then we'll do the second part of this, answer the question on the back, and then talk a little of Chateliers. And hopefully we can get through that. And then I'll speak on the lab reports.